Okay, we've been talking about state space equations, and we've been talking about converting them to different forms of the equation, which are just different representations in state space of the exact same physical system. So this is for a given system, different choices of state variables, and therefore a different set of state equations because the ABCD matrices and vectors will be different given that you have a different choice of state variables. Now, last time we talked about going to a diagonal form, and the way you did that was your transform matrix was the matrix of eigenvectors of the A matrix. And so before I really get into the nuances of diagonal form, I want to just talk quickly about a couple of different forms that are out there. So we've been, as a matter of practice, going to a form known as phase variable form. So we'll review that. And it turns out control canonical form is related to phase variable form, where you just take the state variables and you reorder them. So those two will look very similar to each other. And there are two different forms that are worth discussing: cascade form and parallel form. So I want to go through each one of those and show you how to get to them. And then we'll go back and revisit some of the nuances of the diagonal form. So we're going to start with the system, a transfer function, y over u, and we'll let it be equal to 8 times s squared plus 8s plus 12. So there's our system, and we're going to go through, to start off with, a conventional process of converting that to our state space equations. And again, the state space equations, the cookbook method I've been giving you, is one that puts you into what's known as phase variable form. Alright, so to get started, we're going to multiply this out, and I'm going to sort of do it quickly here. What we're going to do is we're going to say, well, there's a u input, and we'll have a 1 over whatever our denominator polynomial is going to be to get our state, and then we'll have whatever's in our numerator. In this case, it's just 8, and that will give us our output y. So we start by building the expanded block diagram and state space equations for this block here, and then we tack this one on here. So when I do that, I'm going to wind up with an x double dot plus 8x dot plus 12x equals u, and separately I'm going to have a y equals 8x. So when I build that, I'll wind up with two 1 over s blocks, and I have an x dot, an x double dot. I'll put in my summation node. I've got a u coming in to add, and I'm going to have a minus 8 x dot and a minus 12 x contribution in order to get my x double dot. Then I'm just going to multiply it by 8 in order to get y. So there's my block diagram for my standard cookbook technique, which again is going to give me phase variable form. And when I write the equations of motion for this in the state space equations, then I'm going to assume that we have a state vector which is x and x dot, with the highest order derivative on the bottom. Okay, x and x dot. And when we do that, we get an x dot, x double dot, that's our x the vector dot, is going to be equal to our A matrix times x, x dot, plus b times u. And we read off this equation here, we see that the x double dot, I'm going to get a 12 times the x position, I'm going to get an 8 times the x dot position, and I'll have a 1 here. These will actually be negatives, and a 1 for u. And then the x dot is going to equal an x dot, and so I get a first state space equation that looks like that particular form. And then I'll wind up with a second state space equation, which in this case will be our C matrix times x, and we want 8 times x. X is on top, so I'll have an 8 here, and a 0 there, and I have a plus du in this particular case. So here is our representation in phase variable form. Phase variable form. And it is the standard form that we've been using up until now. I just haven't given it a name. And again, you use our cookbook method in order to generate the expanded block diagram and also to generate the state space equations. And in particular, remember that the definition of the state vector is that each state variable is a derivative of the previous state variable. And very specifically, we're going to order the state vector so that the highest order derivative is on the bottom. Okay? Now, it turns out that the second technique, which is control canonical form, is almost identical to state variable form. The only difference is we're going to order the state vector in the opposite direction. So our state vector is going to be x dot x in this case. So in this case, the highest order derivative is on the top, and we go down in a descending order. So what we'll wind up here is essentially the exact same set of equations, but we're going to reorder the state variables, and so it's going to move the values around. And in fact, the block diagram is identical. We haven't changed the block diagram. All we're going to do is we're going to reorder the state variables. And this will give us a set of state equations that looks something like this. X dot x dot x plus pu. And when we do this, what you'll find is we'll wind up with a minus 8 and a minus 12 on the top. The 1 and the 0 will be on the bottom, and we'll have 1 and 0 for a b vector. You can see that effectively what we've done is we've swapped out the rows as well as within the A matrix the columns in order to take care of the effect of having swapped the order of the state variables within the x state vector. And then as a result, we also have a y equals a 0, 8 times our new state vector. And this is control canonical form. We get a rearranged version of the state equations. The block diagram was exactly what it was in phase variable form. My next canonical form is known as cascade or serial form, and what we're going to do is we're going to break up the transfer function and represent it as a serial chain of simpler transfer functions. So here's our transfer function we've been working with, y over u equals 8 over s squared plus 8s plus 12. And before, what we did was we said that we let u come in and affect the denominator polynomial to give us the transfer function to our state, and then from the state through the numerator polynomial give us a transfer function to our output u. We're going to do the same thing here, but first I'm going to factor that denominator polynomial, and when I do that, I'm going to get two first order contributions. I'm going to get an s plus 2 and an s plus 6. Okay? When I see the transfer function like that, now what I'm going to do is I'm going to say in comes a u, and I'll have a what was 1 over the entire denominator polynomial times the numerator polynomial. That gave me from u to x and x to y. And now what I'm going to do is I'm going to break this up into two separate contributions. So this will be a second order. It'll be two first order that are multiplied by each other. So in this particular case, I wind up with a 1 over s plus 2 going into a 1 over s plus 6 going into an 8, and after all is said and done, I wind up with my y. And so if I break this up into an expanded block diagram, I have u coming in, a positive contribution, and I'm going to do the expanded block diagram for a very simple first order system, a 1 over s plus 2 first order system, which is going to look something like this. Subtract off a 2 in the feedback path. And then that is this point here, and so we're going to take that and feed it into a 1 over s plus 6 system. So that adds in 1 over s, and we're going to feed back a 6, negative feedback, like that. And then we're going to multiply that by an 8 in order to get our y. So there is a different way of drawing an expanded block diagram that reflects the exact same system. And before, when we had phase variable form, the block diagram looked completely different. But the equations here are the same, and the block diagram algebra will come out to give us exactly the same transfer function. So in some sense, this is just a restructuring, which is completely equivalent, but gives us different insight into what the system is all about. So in this case, what has happened is we have effectively chosen a different set of state variables. And it turns out that the first state variable is coming out of this integrator, and the second state variable is coming out of that integrator. So we could put together the block diagram algebra and write it in the point of view of x1 and x2 given this representation to get our new set of state variable equations. And that's exactly what we're going to do now. If I have x1 here coming out of the integrator, then it's x1 dot going in. And x2 coming out of this integrator means that that's x2 dot going in. And so I'm just going to use the block diagram algebra to write the equations for each one. And so I have x1 dot equals a positive x2 minus a 6x1. So x2 minus 6x1. And then x2 dot right here equals a positive u minus 2x2. So the u minus 2x2. And at the end I see that y equals 8 times x1. And now to put this into state equation form, I just need to take these same relationships and sort of factor them accordingly. So I'll get x1, x2 dot equals some new version of an A matrix, x1, x2, plus some new version of a B vector times u. So this is x1 dot, x2 dot, that's x1, x2. And similarly, I'll get a y equals some new version of a C vector, x1, x2. And we might as well start off with the y because that's easy. It's just 8x1, so I'll have an 8 here and a 0 there. For the x1 dot equation, I see I have a 1x2. I don't have any x1s. I'm sorry, I have minus 6x1. So I get a minus 6 there and a 1 there, but I don't have any u's. And for the x2 dot equation, I have 1u, and I have a minus 2 times x2, and I have no x1s. And so I wind up with an effective A matrix of minus 6, 1, 0, minus 2, an effective B vector of 0, 1, and an effective C vector of 8, 0. And that is our cascade form. Okay, our final canonical form that we're going to talk about is known as the parallel form. And we'll start off with our same transfer function, 8 over s squared plus 8s plus 12. And what we want to do now is we want to write it in terms of the sum of first order transfer functions. Okay, and we want to keep those same terms. Before we were able to split this into a s plus 2 times an s plus 6. And so I want the same sort of thing, but I want a 1 over s plus 2 plus or minus a 1 over s plus 6 sort of arrangement. And there might be some multiplicative factors thrown in there. But effectively, I want something along the lines of s plus 2 plus an s plus 6 kind of arrangement happening. And I don't know what these numerators are, but I keep the same denominator first order polynomials. So if you work this out, it's sort of like a partial fraction expansion. 8 over s squared plus 8s plus 12. What you need to do is sort of figure out, in general, what the a and the b numerators are if I express the system like this. So I'm going to leave that to you, because this is, again, it's very similar to a partial fraction expansion. It turns out that what we want is a 2 and a minus 2 here. And so that is a 2 s plus 2 plus a minus 2 s plus 6 is going to do the trick. That's going to equal the 8 over s squared plus 8s plus 12. In fact, I'm going to rephrase this a little bit. What I'll do is I'll say that this is a 1 over s plus 2 plus a minus 1 over s plus 6, all multiplied by 2. Now, given this, what we see is we have two first-order systems that are being added together. And then there's a multiplicative factor at the end, just like there has been in all our other forms. So the way I'm going to draw this is, here comes u, my forcing function. Remember, this is y over u. And it effectively says that I'm going to have u times this, and then u times that separately, and I'm going to add them together. So I get a 1 over s plus 2 transfer function, like this. But in parallel, I have a 1 over s plus 6 first order transfer function. It's like u is independently affecting both of these. And the results come out and sum together, and I'm getting a positive contribution from the s plus 2, but I'm getting a negative contribution from the s plus 6. And those go together and are multiplied by 2 in order to get my y. So again, a completely different point of view as to what's going on, but identical math, which means this is just a different perspective, and in reality what this means is we have effectively chosen a different set of state variables. If I expand this fully, u coming up here, then I will wind up with my first order transfer function. I'm going to feed back the 2. Get a plus contribution, a minus 2 feedback like this. And coming down here, have the same sort of construct. I feed back by 6. So here is my 1 over s plus 2 transfer function. Here is my 1 over s plus 6 transfer function. They're going to come down and up, and one's going to add and one's going to subtract. And then there's my multiplicative factor in order to get my y. Now we know that the state variables are the variables coming out of the two integrators. So here is an x1 and here is an x2. And if this is x1 and that's x2, then there's x1 dot and there's x2 dot. And I can write the equation for each of those, which is what I'm going to do now. Here's the x1 dot, here's the x2 dot. And so we're just going to do what we've been doing before in order to generate our state variable equations. So I've got an x1 dot is equal to a u minus a 2x1. And I have an x2 dot